Continuing with section 4.4, we now move on to example 3. And above the example we see, if the base e appears in an exponential equation, solve the equation using natural logs. So if you have an exponential equation with a base of e, then you definitely want to use natural logs to solve that equation. As in an earlier example that we did, before we apply a natural log, we want to isolate the exponential part of the equation. So in example 3, we see the exponential expression e to the minus t over 2. So we want to isolate that by dividing first both sides by 3. E to the minus t over 2 equals 2/3. Now, with 2/3 being a repeating decimal, I'd rather not write that as a decimal, say as 0.67 or something like that. I'm just going to leave it as a fraction. This helps to preserve better accuracy in my answer, in my solution. Once I've isolated e to the variable power, then I apply natural logs to both sides, just as we did in our earlier examples. I'll put the 2/3 in parentheses here. And then one nice thing about having a base of e is that if you use a natural logarithm, we have this cancellation or inverse property. ln of e to the x equals x for any x. So in this case, we can essentially just cancel ln and e, since they're inverses of each other, and that would just simply give us on the left minus t over 2. So the logarithm vanishes from the left-hand side. Then to solve for t, the approach here would be to multiply both sides by -2. So t would be -2 times the natural log of 2/3. That would be the exact answer. And then using a calculator, we can approximate that. And you should verify that the approximate value is 0.81. You might be surprised that the solution here actually is a positive number, since you see a negative sign out in front. But that's due to the fact that the natural log of 2/3 itself is a negative number. So actually what you're doing here is multiplying -2 by another negative number, and that's why you end up with a positive number when you approximate it. We'll now consider what are called logarithmic equations. An equation that contains expressions of the form log base a of x, so containing logarithmic expressions, is called a logarithmic equation. Since log base a of x is defined only when x is positive, greater than 0, we must always check proposed solutions of logarithmic equations for possible domain violations. We want to make sure that when we substitute our proposed solution back into the original equation, that we don't end up with logarithms of 0 or negative numbers, which are going to be undefined expressions. So we have to pay attention to the possibility of extraneous solutions, that is, values that come out of the solution process that are not actually solutions of the original equation when we're solving logarithmic equations. This is not something that comes up with exponential equations, but it can come up with logarithmic equations. If both sides of the equation can be expressed in terms of the same single logarithmic function, then it's possible just to drop the logarithms from the equation. If we look at example 4, we have the equation log base 4 of 2 plus log base 4 of x equals log base 4 of x minus 3. What you do not want to do is simply cancel the logarithms off and write 2 plus x equals x minus 3. That's going to be incorrect. what we have to have before we remove logarithms is a single logarithm on both sides of the equation. So what that means in this case is that with the two logarithms on the left-hand side, we need to combine them as a single logarithm. We can do that using the product rule for logarithms, which says that a sum of logarithms can be written as a single logarithm of a product. So on the left-hand side, we would write log base 4 of 2 times x. So a sum of logarithms, where the logarithms are of the same type, they have the same base, can be expressed as a single logarithm of a product. Now on the right-hand side, there's only a single logarithm to begin with, so I'll just rewrite that. Now, because of the fact that logarithmic functions are one-to-one, that is, if the y values are the same, if the function values are the same, then the, so to speak, x values have to be the same. We can drop the logarithms altogether here and just write 2x equals x minus 3. So I can only remove the logarithms after I have a single logarithm on both sides of the equation. So if you have sums or differences, those will have to be expressed in terms of a single logarithm using either the product and or quotient rules for logarithms. All right, then if we subtract x from both sides, and it just occurs to me, we get x equals negative 3. I'm going to have to change this. I don't want to end up with an equation to start off with that doesn't have a solution. This actually would not be a solution because it violates our domain restriction of x being greater than 0. I kind of hate to start out with one like that, so I don't normally do this, but let me just change this problem a little bit. Let's make this x plus 3. X plus 3, x plus 3. This would be x plus 3. So let's assume that we get positive 3 for our answer. I'm sorry about that. That's just something I just noticed after I had set everything up here. This would indeed be a solution of the original equation. Now you're not allowed to do that on the test. Sorry about that. To change the equation to suit your purposes. But in this case, I hope you don't mind if I do that, just to give us an equation that actually has a solution. If our logarithmic equation can be written in such a form as log base a of x equals b, so we don't have a logarithm on both sides of the equation after we simplify, then we need to convert to exponential form. We need to remove the logarithm by converting it to an equivalent equation in exponential form. And we do this, as you may recall, by starting with the base, raising it to the b as the exponent, and then setting it equal to whatever is inside the logarithm. So a to the b equals x. So I'll demonstrate that with the examples in example 5. Log base 3 of x plus log base 3 of x minus 2 equals 1. First of all, I want to have a single logarithm on the left-hand side. So I'm going to use a product rule as I did in the previous example, and write log base 3 of x times x minus 2. Set that equal to 1. Okay, now we could multiply the x and the x minus 2 together if we wish, or we can just leave it as a product x times x minus 2, which is what I'll do. Now let's convert this to exponential form. The exponential form, start with a base of 3, raise it to what the logarithm is equal to, raise it to the first power, set it equal to what's inside the logarithm. That is x times x minus 2. Okay, now the right-hand side is in a factored form, but that factored form isn't really going to be of any use to us in solving the equation, so we actually need to multiply that out. That's due to the fact that the left-hand side is not equal to 0. So the left-hand side is 3. The right-hand side is x squared minus 2x. If I set this to 0 by subtracting 3 from both sides, I obtain a simple quadratic equation. If I factor x squared minus 2x minus 3, I obtain x minus 3 times x plus 1. Then setting those factors each equal to 0, we would obtain x equals 3 or x equals negative 1. Well, x equals 3 does not create any domain issues when we substitute it back into the original equation. So x equals 3 is definitely a solution of this equation. But x equals negative 1, whether you substitute it into the first logarithm or the second one, is going to end up giving you the logarithm of a negative number. And so here is an example, sort of the first example, but I guess in a sense the second example. But our first official example of an extraneous solution. So we need to just discard that as a solution. So this equation has only one solution, x equals 3. So this is quite typical with logarithmic equations. You have to pay attention to the fact that logarithms are only defined for positive numbers. So if you obtain a solution that would end up giving you the logarithm of a negative number, you have to discard it. The logarithm of a negative number or the logarithm of 0. Logarithms are only defined for positive numbers. Alright, I'm going to need one more video to complete this set of notes, and if I start, I have time to start example 5 part B, but probably not time to finish it in this video. So let me just conclude this video and we'll complete the notes in the next video.